So I'm gonna present a bit quickly because I think so we are run out of the time. So my objective in this talk was basically differentiate between models and simulations to in the future scientists that works on artificial life and artificial chemistry and better how they can build up models and to be implementable in laboratory situations. So I will start by describing quickly what is the modeling relation and the current situation of science. So science is based on this graph. So we have a natural system that can be alive or not. And the natural system has its own causal elements, as we can see at C. So we can measure, observe, and encode this causality of the natural system into a formal system that has its own inferential entailments. When this formal system can predict, postdict, or realize the natural system, we can say that we have a model of that natural system, that the formal system F if the model is the model of the natural system N. So for example, we have a table as a natural system that it is not alive. What will be the model, the causal entailment of the table? The table is not a chair, it's not other object, just a table, it's a board with either a central or peripheral support. So once we encode the causality of a table as a board with either a central or peripheral support, so with its own inferential entailment, we can use already the formal system to realize any kind of tables. So the model, it's important that in the model, in the decoding, there is also a kind of realization. So based on the model on a board with either a central or peripheral support, we can already fabricate and build up tables of different materials. So it can be metal, plastic, different things. So then when we have this situation, we can say that the model became a natural law, that we need only the model to surrogate any natural system of that belongs to that model. So this happened when Newton captured the causality of natural systems that are not alive. So he encoded in a formal way the causality as a force-time sequence state-determined dynamic transitions. So basically, we have initial conditions and change the evolution of the system changed to time state by state. So this is the inferential entailment, which was very powerful to predict, postdict, and describe natural systems that are not alive, and therefore became a natural law. But the state causality framework of Newton, it does not become realization of living beings. So we can describe some behaviors of living systems, of natural systems that are alive, but we cannot construct them based on the dynamical laws of Newton. The issue is that at this moment, the state transitions, this framework to capture causality as state transitions became the causality of all natural systems. So living or not living, because we can describe also living systems with the dynamical laws of Newton, we consider that the natural system itself, it's not anymore the natural system, it's the formal system that Newton puts forward. So we depart at this moment on science by thinking that the causality of all natural systems has this form, and from this form we started to encode new formal systems. So the current situation is basically like that. So we at this point we forget the natural system itself when we are talking about living systems, and we consider that the causality of that natural systems is itself the dynamical laws. And then from the dynamical laws, we started to encode new formal systems that are algorithmic, that are Turing computable things. So the situation is that organisms became a subset of machines, which became a subset of physical systems. So this vision has challenged by Robert Rosen, which some people call the biologist Newton, that he's the biologist Newton. Why? Because in the formal system, we can ask of the Newton, why x1 or b in this case? And it has two sort of answers. So because x0, which is the material code, the initial condition, and we can say because of F, the efficient cause and the dynamical equations. In the dynamical equations also we can find parameters. So we can say, but we are gonna drop. The parameters could be the formal cause. So we can find in the Newton law, we can find material cause, efficient cause, and formal cause as parameters. So the causality of Aristotle's get out. When the question why F, when we ask the question why F in this formal system, in physics has no real answer, in the actual physics, in the current physics, and therefore in the actual way of modeling things. By contrast, in biology, as Rosen showed, the why F does have an answer from within the system. How he showed that? So he considered that the causality of living things is not state transition. So even though we can describe by dynamical laws some behaviors of living systems, the causality of them is not reduced to that. And the causality of a living system, as he said, is a material system, is an organism if and only if it's closer to efficient causation. What means that? So just take a minute here. So we have a model that he built up. So we have a transformation of metabolites from A to B, which has an efficient cause called F. So F acts on A to transform into B. So he asked, who produced, why F? Who produced F? So he said, okay, it needs to be another efficient cause called phi that acts on B to produce F. Then the other question was, why phi? Why phi? And this brings us to an infinite regress. But mathematically, he found that inverse map of B could act on F to produce phi. So in that sense, the system is closest to efficient causation. So we don't need anything from outside the system to the system build itself and fabricate itself. So Robert Rosen considered that the model of living things is this one. And then we have this situation. So we have a natural system and we have two formal systems, which can be compatible each other, not compatible indirectly, but complementary, I will say, complementary. And we can consider that the formal systems of Newton are just simulations because describes, while the model of Rosen, the formal system of Rosen, is a model that explains the causality of living systems. Why I say that? Because we can ask what is the final cause of F. And we can say that the final cause of F is produce B. So within the system, within a system that it is close to efficient causation, we can find final causation. And final causation, it's called as well teleology in some way. And it's called also goal-directed behavior. So in the model already, we can find anticipative behavior because to produce certain kind of B, a subset of B, the system needs to know what kind of A will take from the environment, and so on and so forth. So what Rosen presents, is that indeed organisms are physical systems, but are not a subset of machines. So this is, of course, opens a new window at mathematical level in physical system to enlarge physics. Somehow, what Schrödinger was saying, the new physics. And then we have the situation where simulation is not a model. And I'm not going to enter into details, into mathematical details, but you can write me to share bibliography. Based on this, we have different publications that a material realization of Rosen's model, for instance, have no computable models, and that a living system will have no computable models. Or recently, that the situations of kind of the MR system, that things that produce itself, can be undecidable under the machine learning experiments. So models are not sophisticated kind of curve fitting. The assertion that since a given curve can be approximated by a polynomial, it must be a polynomial, could be a situation of simulation. Stated otherwise, curve fitting without a theory of the shape of the curve is simulation. Model requires understanding of how and why a curve takes its shape. Any question that you have or any reference that you will want, you can write me down. And also I will take profit of this presentation to invite you to submit some papers to a special edition that I am editing. And I am open to questions.